Hi everyone, I would like to thank the organizer for the opportunity and comment my English is not good, but I will do my best, okay? So today I'm going to talk about explicit equation for maximal curves, a subcover of the VM curve, the Billin-Montanucci curve, and this is a joint work with Luciane Quos, okay? So first, I am going to introduce the notation and some previous results. For example, FQ denotes the final field with Q elements. X is an irreducible, not singular projective curve of genus G defined over FQ. FQX denotes the function field of the curve X. And the Hasse-Weil bound states that the number of FQ rational points on the curve X is less than or equal to this expression. This, okay? In particular, the curve X is called FQ maximal if this number attains the Hasse-Weil bound. In addition, we have the following important and fundamental results. If X is a maximal curve and Y is a subcover of X, that is, we have the following inclusion of function fields, then Y is also maximal. So this result provides a way to obtain new maximal curves from no maximal curves. How? For example, if we have a maximal curve X and its automorphism group, we can identify a subgroup, for example, H of the automorphism group of X, and we can calculate the fixed field of H. The fixed field of H is defined by this set. Is the set of elements in the function field of the curve X, such as sigma C equals C for all elements in H. This set is a subset of the function field of X. Okay? So this fixed field of H is a function field of a curve called the quotient curve of X corresponding to the subgroup H. So that is, there X is a curve Y, for example, such as the fixed field of H is equal the function field of the curve Y. This curve Y is called the quotient curve of X corresponding to the subgroup H. So by this result, this quotient curve is also maximal. The problem here is that is to find an explicit equation for this quotient curve. This problem is often complicated, but why is important to have explicit equation for maximal curves? For its application in other areas, such as coding theory and finite geometry, for example. On Wednesday, Alonso Sepúlveda and Maria Brasamorós talk about algebraic equation codes. To construct algebraic equation codes with good parameters, we need maximal curves or explicit equation for maximal curves or explicit equation for curves with many rational points, okay? So some example of maximal curves, we have the Hermitian curve, is defined by the following algebraic equation. This curve is maximal over FQ squared. A few years ago, all examples of maximal curves were a subcover of the Hermitian curve, and recently, in 2009, Juliet and Kochmar construct the third example of maximal curve not covered by the Hermitian curve. This is the GK curve, and is defined by the following equation. This curve is maximal over FQ6. And 1 year later, Garcia, Guarneri, and Stirnots presents the first generalization of the GK curve. This is the GGS curve, and is defined by these equations. This curve is maximal over FQ power to R, and when R is equal to 3, we obtain the GK curve. So in 2016, Giulietti, Quos, and Cini introduced a new model for the GK curve. This new model is given by these equations. And in the same work, the authors provide several families of quotient curve for the GK curve. Okay? So calculate, in some cases, the genus and the subgroup corresponding to the quotient curve. So in 2018, using this model introduced by Giulietti, Quos, and Cini, Belen and Montanucci present a second generalization of the GK curve. This is the BM curve, and is defined by these affine equations. This curve is maximal over FQ power 2R, okay? And in this work, we present two new models for the BM curve. From the automorphism group of the first model, we identify subgroups to construct new families of quotient curves. And as a consequence, we generalize several families of quotient curves given by Giulietti, Quos, and Cini. Also, from the symmetry of the equation of the second new model, we obtain new subgroups of the automorphism group of the BM curve, and therefore we obtain new families of quotient curves. As a consequence, we get new example of maximal curve not covered by the Hermitian curve. Okay? So to obtain the first new model of the BM curve, we apply the following morphisms to the curve given by Giulietti, Quos, and Cini, obtaining this curve X. This curve X is a new model of the GK curve. And next, we consider the natural generalization of the curve X. So we replace this exponent by M, where M is equal to this quotient, and we obtain this new curve, the curve XR. This curve is isomorphic to BM curve, and its automorphism group is given by this set. The idea now is to identify subgroup of this automorphism group to construct new families of quotient curves. So, for example, here we present a first family of quotient curves. For this, we consider D1 and D2 divisor of Q plus 1, and D a divisor of QR plus 1, satisfying this condition. Okay? And we consider the following subgroup H. So, in order to obtain the quotient curve corresponding to the subgroup H, we define the following functions. And after some computation, we can verify that these functions satisfy the following algebraic equations. Okay? So now, we are going to prove that the equation y defined by this algebraic equation, the curve y defined by this algebraic equation, is the quotient curve of corresponding to the subgroup H. So for this, note that these functions are in the fixed field of H, and therefore we have the following inclusion of function fields. So also, as this extension is Galois, then its degree is equal to the cardinality of H. In this case, is equal to this quotient. And on the other hand, from the equation that defines the curve y, we obtain that this extension, the degree of this extension, is less than or equal to the subgroup, the cardinality of subgroup H again. Okay? So from this inclusion of function fields, we conclude that the function field of the curve y is equal to fixed field of H. So this implies that the curve y is the quotient curve corresponding to the subgroup H. Okay? So to calculate the genus of this family of quotient curves, it is sufficient to know that the equation that defines these quotient curves are Kummer extension, and therefore we can use the Riemann-Hurwitz theorem to calculate the genus. In this case, the genus is given by this formula. Okay? This first family of quotient curves is generalized the family of quotient curves given by Giulietti Cosenza. And in this work, we calculate the genus and the subgroup corresponding to the quotient curve in all cases. The unique condition is this GCD. So for the second new model of the BM curve, first we consider an element in the field with these conditions and consider the following morphisms. So we apply these morphisms to the curve XR, that is the first new model of the BM curve, and we obtain this a second new model of the BM curve, the curve FR, with the following automorphism group. Okay? So the problem here is that with this description of the automorphism group, it is complicated to identify subgroups to construct new families of quotient curves. But from the symmetry of the function x and y in this equation, we can identify some automorphisms and consider the subgroup generated by them to construct new families of quotient curves. For example, for the divisor of q minus 1, d2 divisor of m, we consider the following automorphisms. Okay? The subgroup generated by this automorphism is a subgroup not considered before, and therefore for this subgroup, we obtain new families of quotient curve. These families of quotient curve is given in the following results, in the following theorem. And note that, in this case, the equations that define this family of quotient curves are no Kummer or artificial extension. Therefore, the calculation of the genus is not direct. But it is possible to decompose the function field of this quotient curve into a tower of function fields composed only by Kummer or artificial extension. So with this, we can use, again, the Riemann-Hurwitz theorem to calculate the genus. Okay? In this case, the genus is given by this expression. And finally, as a consequence of this theorem, we obtain new example of maximal curves not covered by the Hermitian curve. In fact, for example, for r equal to 3, d1 equal q minus 1, and d2 equal this quotient, where k is in this interval, okay? The quotient curve obtained in the previous result is not covered by the Hermitian curve. The main reference for this work is the following. In the first reference, Giulietti Cosenza present a new model for the GK curve and several families of quotient curves. In the second reference, Billin and Montanucci using this model of the GK curve given by Giulietti Cosenza to construct a second generalization of the GK curve. And in the last reference, we present the result in this talk and some additional results. Okay? Thank you for your attention.